So the theorem we have here is the monotone convergence theorem, and this theorem is really nice because we can talk about a sequence converging without actually knowing its precise limit. And so the monotone convergence theorem states that if a sequence is monotone and bounded, then it converges. Recall that a sequence, let's call it xn, is monotone if it is either increasing or decreasing. And xn is increasing if xn is less than or equal to xn plus 1 for all n in natural numbers, and xn is decreasing if xn is greater than or equal to xn plus 1 for all n in the natural numbers. Alright, so how about the formal proof? Suppose sequence xn is bounded and increasing. We'll assume that it's increasing here, but for the decreasing case, it will be very similar. So I encourage you guys to try it on your own after this. All right, so suppose the sequence xn is bounded and increasing. There exists let S be the supremum of the set of all the elements in the sequence. And we are allowed to say this because the set of all elements with the sequences inside is non-empty, and it is certainly bounded by m, some number m greater than 0. So we can let S to be the supremum of a set of all elements where the elements are the terms of the sequences. All right, then let epsilon greater than 0 be given. Then there exists xn element of the set we have such that S minus epsilon is less than xn. And this is just the definition of supremum. Recall we had a lemma we proved before that if S is the supremum of a set, then there exists an element in that set such that S minus epsilon is less than that element. All right, then since the sequence xn is increasing, xn is greater than or equal to x big N for n greater than or equal to n. All right, then we have S minus epsilon being less than x big N, which is less than or equal to xn. Well, since S is an upper bound for the set of all the terms in the sequence, we know that xn is less than or equal to S. But that S is, again, less than S plus epsilon. So we have that for all, whenever small n is greater than or equal to big N, it follows that xn is greater than S minus epsilon and xn is less than S plus epsilon. Well, this implies that xn minus S is less than epsilon whenever n is greater than or equal to n. Hence, xn converges. And that's the end of the proof. So we use the fact that the sequence of xn is bounded to justify having a supremum of the set of elements where the elements are the terms of the sequences. And we use the fact that the sequence is increasing to show that all terms after the big N are going to be greater than or equal to the terms of xn, which is shown here. Well, the fact that S is an upper bound for the set of the elements of the sequences, we know that xn is going to be less than or equal to s. And since epsilon is just an arbitrary number greater than 0, we know that s plus epsilon is going to be greater than s. Hence, we have that the terms of the sequence xn is going to be in between s minus epsilon and s plus epsilon. So that allowed to conclude that the absolute value of xn minus s is less than epsilon whenever small n is greater than or equal to the big N. Well, that's the exact definition of a convergence of a sequence. Hence, we know that if a sequence is bounded and monotone, then we know that the sequence converges.